Hello, this is Chitali Acharya, and today I am attempting to explain decision tree algorithm. So, first of all, what is decision tree? So, a decision tree is a flowchart-like tree structure where internal node represents a feature or attribute, and the branch it shows a decision. The leaf shows the outcome. So, basically, it's an algorithm which has a representation like this. So in machine learning, decision tree is a supervised learning algorithm. Most of the time, the data, the features and the target variables are generally provided. And it can be used for both regression as well as classification kind of problems. So if we see here, this is a tree format and there are certain decisions that are to be made. So we are looking into people who either died or survived. Okay. And what do we have in the data? Is the person a male or a female? Is the age greater than 9.5 or less than 9.5? Does the person have any siblings or spouse? Based on these, we are making our decisions whether the person died or whether the person survived. So basically, decision tree algorithm makes these kind of decisions. So how does this algorithm work? So basically, we need to create the decisions in the first step. Then select the various attributes. And how are we going to do that? Using certain statistical measures. Make the attribute as a node and then break the tree into smaller data sets. And then start the tree building process recursively for each child. It may appear difficult here. Let's start with a simple example. So here is our problem set. Okay, so it's a zoo-based data set which identifies species as mammals, reptiles. This is our data. So the first thing that we need to do is create decisions. So what could be our decisions in such a data? The decisions could be whether the species is toothed or not. That is, it has teeth or not. Does the species has hair or not? Does the species breathe or not? Does the species have legs or not? And based on these decisions, we can decide whether the species is mammal or animal. So if I give you to prepare this tree, how would you do that? How would you decide what would be the top of the tree over here and what would subsequently fall into the branches? So for that, we use the second thing, an attribute selection measure. And statistics provide us with two measures, information gain and Gini index. So information gain, it basically measures the reduction in entropy. And entropy is the different randomness that you can see in a data. So in simple format, the formula is for entropy, summation of the probability of the feature into log 2 of the probability of the feature. So let's consider our current example and let's begin with this. So the entropy of the species node goes as 6 by 10. So let's have counting. So we have total 10 features, so 0 to 9. Let's count the mammals 1, 2, 3, 4, 5, and 6. And needless to say, the reptiles would be 4. So entropy formula would be 6 by 10. That's the probability of mammals into log 2 6 by 10. Similarly, 4 by 10 is a reptile. So 4 by 10 probability into log 2 of 4 by 10, that gives us 9.71. Now we remove entropy of each and every feature over here. So entropy for tooth, true. Entropy for tooth, false, respectively using the same formula. Then we can find the entropy for split, that is for truth and for false. And then we find the information gain, which is entropy of the parent node, that is 0.971, minus average entropy of the children, that is 0.96, and that gives us 0.001011. So similarly, we calculate the entropy for all the things, that is for breaths, for lungs and everything. And once it is done, we see that out of all these, legs has the maximum information gain. And that is how we selected what would be the root of our tree. So legs is a root of our tree, followed by tooth, followed by breath, and that is how the data gets divided at each set, giving us a tree. Isn't that interesting? So that is the first way of calculating the root. So we created the decisions. We first, that is whether the animal is tooth or not, hair or not, breathes or not, has legs or not. Then we used a statistical approach to see what could be the tree root of our decision. And then we created the nodes. So our nodes would be first with legs, followed with tooth, then with breathe, and recursively our algorithm would keep on working. And finally, once it is done, so once we have all the attributes in place, we no more have to split the tree. Similar to entropy, we have Gini. So the basic idea over here is that everything falls into the same bucket. So you basically divide everything into similar kind of buckets. Okay. So if we select two items from a population at random, then they must be of the same class and probability. And that is how you say that that population is pure. So Gini works good with categorical variable like success failure. It performs very well in binary splits. And higher the value of Gini, higher the homogeneity. So for Gini, the formula is 1 minus summation of all the probability squared. So it's pretty similar to that of entropy. And just like entropy, we calculate Gini for each and every node. Yes. And based on similar to information gain, we calculate the Gini gain. And similarly, we decide what will be the root of the tree, what would be the subsequent nodes and branches. So we calculate the Gini before split, the Gini after split, and then we calculate the Gini gain. Now, an interesting thing with decision trees is to find out bias and variance. So if we see what we did over here is for every node, we calculated what would be the gain for every particular feature, for tooth, for hair, for breath, for legs, and similarly for that is we did it for information gain and also for Gini index. Now, our algorithm learned totally everything about all the features one by one. This means every time I introduce another column, the algorithm will completely learn about all the values of that column. This would mean that the algorithm would be more prone to overfitting because it learned too much with my data. Now, this would be the problem that if I split my data into two halves, training data, testing data, then the algorithm would completely learn more about the training data and would perform bad on the testing data because it learned the training data too well. That would be an overfitting problem. And algorithms with overfitting problem mostly result into having very high variance and a low bias. And that is why decision trees suffer with high variance, most of the times with high variance and low bias. So it's always good if we select the parameters, if the bias variance ratio is somewhere in the middle, not too high, not too low, to give good features. So decision tree algorithm in a nutshell is simply a supervised classification and regression algorithm, and it uses statistical approaches like entropy and information gain in the backend. Another thing with decision trees is that it works well with categorical variables, also with continuous variables, but then we need to convert the continuous ones into some categorical variables using ordinal encoders or some kind of encoding. So all the classification problems such as finding if the email is spam or not, if the tumor is cancerous or not, all of these can be, decision tree can be applied on them. If you're not looking for a too complex model, decision trees work well. Of course, with too many features, yes, the cost would be high because we would be finding the best split every time. So yes, with too many features, it would be difficult to use the decision trees, but with proper bias variance ratio, we should be able to do it. So this is all that explains decision trees in a small nutshell. Thank you.